Hi, in this session we discuss about some examples which is an application of Sylow theorems. The first example is any group of order 40 has a non-trivial normal subgroup. We know that, or we have seen in the last session that if G has a unique Sylow P subgroup, then that subgroup is normal. So here also we have to find a unique Sylow P subgroup for some P. So let G be a group of order 40 and 40 is equal to 2 cube into 5. So therefore G has a Sylow 2 subgroup and a Sylow 5 subgroup. So let N5 is equal to the number of Sylow 5 subgroup of G. Then N5 divides index of P in G, where P is a Sylow 5 subgroup. So therefore N5 divides order of G upon order of P, which is equal to 40 upon 5, which is equal to 8. That means N5 divides 8. But by third Sylow theorem, N5 is equal to 1 plus 5t for some t greater than or equal to 0. So this means that 1 plus 5t divides 8. That means this is possible only if t is equal to 0. That means N5 is equal to 1. Therefore, the number of Sylow 5 subgroup of G is 1. That means G has a unique Sylow 5 subgroup, and so it is normal in G. Therefore, G has a non-trivial normal subgroup. For proving some of the remaining examples, we need the following lemma. The lemma states that if H and K are finite subgroups of a group G, then the number of elements in HK is same as order of H into order of K divided by order of H intersection K. It is, if H and K are subgroups of G, that does not mean that HK is a subgroup of G. So it says that even if HK is not a subgroup, we can find the number of elements in HK, which is same as number of elements in H into number of elements in K divided by number of elements in H intersection K. By definition, HK is equal to the set of all elements of the form small h into small k, where small h belongs to H and small k belongs to K. So let cardinality of H is equal to R, or order of H is equal to R, and order of K is equal to S, and order of H intersection K is equal to T. So we need to show that the order of or cardinality of HK is equal to R into S upon T. So now since H contains R elements and K contains S elements, HK contains at the most RS elements. That means the number of elements in HK is less than or equal to RS. But it is possible that H1 K1 is equal to H2 K2 for some H1 H2 in H and K1 K2 in K. That means there may be some repetitions. So if H1 K1 is equal to H2 K2, then H is equal to H2 inverse H1, which is equal to K2 into K1 inverse. So if we take H is equal to H2 inverse H1, then H belongs to H because H1 and H2 belongs to H, and H is a subgroup of G. Similarly, if H is taken as K2 into K1 inverse, then H belongs to K because K1 and K2 are in K, and K is a subgroup of G. So this means that H belongs to both H and K. That means H belongs to H intersection K. Therefore, we can write H2 is equal to H1 H inverse and K2 is equal to H K1. That means that if H1 K1 is equal to H2 K2, you can always find an element H in H intersection K such that H2 is equal to H1 H inverse and K2 is equal to H into K1. On the other hand, if Y belongs to H intersection K, and if you define H3 is equal to H1 Y inverse, that is an element of H because H1 is in H and Y is also in H. And K3 is, if we define K3 is equal to Y into K1, it belongs to K. So clearly H1 K1 is equal to H3 K3. That means that for any Y belongs to H intersection K, we can find H3 belongs to H and K3 belongs to K such that H1 K1 is equal to H3 K3. So this means that any element Hk can be repeated, or Hk can be represented as Hi into Ki for where Hi is in H and Ki is in K, for it can be represented in that one for number of times. That number of times is equal to the number of elements in H intersection K. That means Hk can be repeated in capital Hk for t times, where t is the number of elements in H intersection K. Therefore, every element of Hk is repeated for t times. Therefore, the cardinality of Hk is same as R into S upon T, which is equal to order of H into order of K upon order of H intersection K. So we now show that any group of order 15 is cyclic. So let G be a group of order 15. 15 you can write it as 3 into 5. So G has a Sylow 3 subgroup and a Sylow 5 subgroup. Let N3 denote the number of Sylow 3 subgroup of G. So N3 divides index of P in G, where P is a Sylow 3 subgroup. Therefore N3 divides 15 by 3, which is equal to 5. But you know that by third Sylow theorem, N3 is equal to 1 plus 3t for some t greater than or equal to 0. So therefore 1 plus 3t divides 5. And this is possible only if t is equal to 0. So in this case, when t is equal to 0, N3 will become 1. Therefore, G has a unique Sylow 3 subgroup. Let the subgroup be H, then definitely order of H is equal to 3 and H is normal in G. Similarly, we can show that G has a unique Sylow 5 subgroup. Let the subgroup be K, then order of K is equal to 5 and K is also normal in G. Now since H intersection K is a subgroup of both H and K, order of H intersection K divides order of H and order of K. That means order of H intersection K divides 3 and 5. Therefore, order of H intersection K divides GCD of 3 and 5, which is 1. That means order of H intersection K is equal to 1. This means H intersection K contains only one element, namely identity. Also note that order of H into order of K is equal to 3 times 5, which is 15, and that is same as the order of the group. Therefore, by previous lemma, the cardinality of Hk is equal to order of H into order of K divided by order of H intersection K, which is same as order of G. But Hk is a subset of G, and the number of elements in Hk and number of elements in G are same. Therefore, Hk is equal to G. Thus, we have three things. One is H and K are normal subgroup of G. Second is H intersection K is identity. And third is G is equal to Hk. Therefore, G is the internal direct product of H and K. That is, G is isomorphic to H cross K. Since order of H is 3 and 3 is prime and any group of prime order is cyclic, therefore H is cyclic. And since any cyclic group of order n is isomorphic to Zn, H is isomorphic to Z3 because H is a cyclic group of order 3. Similarly, K is isomorphic to Z5. Therefore, G is isomorphic to H times K, which is isomorphic to Z3 times Z5. Because the GCD of 3 and 5 is 1, we have Z3 cross Z5 is isomorphic to Z15. Therefore, G is isomorphic to Z15. That means that G is a cyclic group of order 15. That means G is cyclic. So following is a generalization of above example. Here G is a group of order PQ where P and Q are primes, P is less than Q and P does not divide Q minus 1. Then G is a cyclic. So in the previous example, order of G is equal to 3 into 5 where 3 is less than 5. 3 does not divide 5 minus 1, that is 4, and we have shown that G is a cyclic. The same or similar argument can be worked here also. So for the completeness, I am giving the full proof of this one or full solution of this question. So let H be you know that G is a group of order PQ and P is a divisor of G and Q is also a divisor of G. G has a Sylow P subgroup and a Sylow Q subgroup. Let H be a Sylow P subgroup of G and K be a Sylow Q subgroup of G. Therefore, the number of Sylow P subgroup of G is 1 plus Tp and that divides Q because it divides the index of P in G which is equal to Q. Therefore, 1 plus Tp is either is equal to 1 or 1 plus Tp is equal to Q. So if 1 plus Tp is equal to Q, then P divides Q minus 1, which is not possible. Therefore, 1 plus Tp is equal to 1. Therefore, G has only a unique, only a single or only a one Sylow P subgroup of G. That means H is the only Sylow P subgroup of G. Therefore, H is normally G. Similarly, we can show that there is only one Sylow Q subgroup K of G and therefore K is normal in G. Since H intersection K is a subgroup of H and K and so order of H intersection K divides both P and Q, so it divides GCD of P and Q which is 1. That means order of H intersection K is equal to 1. Therefore, H intersection K is equal to only identity. Also, order of H into order of K is equal to P into Q which is equal to order of G. Therefore, order of HK is equal to order of H into order of K upon order of H intersection K which is same as order of G, which implies HK is equal to G because HK is a subset of G and the number of elements in HK and number of elements in G are same. Therefore, G is equal to HK. Thus, we have three things. One is H and K are normal subgroup of G. Second is H intersection K is identity. And third is G is equal to HK. Therefore, G is internal direct product of H and K. That is, G is isomorphic to H cross K. So since order of H is equal to P and P is prime, and we know that any group of prime order is cyclic, therefore H is cyclic, and since order of H is P, H is isomorphic to ZP. Similarly, K is isomorphic to ZQ. Therefore, G is isomorphic to H cross K, which is isomorphic to ZP cross ZQ. And since GCD of P and Q is 1, ZP cross ZQ is isomorphic to ZPQ. That means G is isomorphic to ZPQ and therefore G is a cyclic group. So we proved that if G is a group of order PQ where P is less than Q and P does not divide Q minus 1, then G is a cyclic. Now we show that any group of order 11 square into 13 square is abelian. Let G be a group of order 11 square into 13 square. Let N11 denote the number of Sylow 11 subgroup of G. But we know that N11 is equal to 1 plus 11t for some t greater than or equal to 0. Therefore, 1 plus 11t divides 13 square. And this is possible only if t is equal to 0. Therefore, n11 is equal to 1. Therefore, G has only one Sylow 11 subgroup in G. Let this subgroup be P. Then, because it is unique, that subgroup is normal in G. That means P is normal in G. Similarly, G has only one Sylow 13 subgroup, say Q, and is normal in G. Since any group of order P square is abelian, P and Q are abelian. And since P intersection Q is a subgroup of P and Q, implies order of P intersection Q divides both 11 square and 13 square. So it divides the GCD of 11 square and 13 square, which is same as GCD of 11 and 13, and which is same as 1. That means order of P intersection Q is 1. So that is P intersection Q contains only one element, namely the identity element. So therefore, the number of elements in PQ is same as order of P into order of Q upon order of P intersection Q, which is equal to 11 square into 13 square upon 1, which is equal to 11 square 13 square, which is equal to order of G. That means the number of elements of PQ and G are same. But PQ is a subset of G, and they are both the set having the same number of elements, which implies G is equal to PQ. Now for A is in P and B is in Q, X is equal to AB A inverse B inverse. That I can write it two different ways. One is AB A inverse into B inverse, and the other one is A into B A inverse B inverse. Suppose X is equal to AB A inverse into B inverse. Since B is in Q and A is in G and Q is normal in G, AB A inverse belongs to Q. And already B inverse is also in Q, so their product is in Q, so X is in Q. So if I take X is equal to A into B A inverse into B inverse, then as A inverse is in P and P is normal in G, B A inverse P inverse must be belongs to P. And since A is also in P, A into B A inverse B inverse also belongs to P. Therefore, X belongs to both P and Q. But P intersection, therefore X belongs to P intersection Q, and P intersection Q contains only one element, that is E. Therefore, AB A inverse B inverse is equal to E, which implies that AB is equal to BA. That means any element in P and Q commute. So since G is equal to PQ and the elements of G are the elements of the product of the element of P and Q, and P and Q are abelian, therefore, and among P and Q, that means if A is in P and B is in Q, AB is equal to BA. Therefore, every element of G must commute. Therefore, G is abelian. The following is the generalization of the example. So that one says that let G be a group of order P square Q square, where P and Q are distinct primes. Q does not divide P square minus 1 and P does not divide Q square minus 1. Then G is abelian. The proof is similar to the previous example. So for the sake of completeness, I am just giving the proof in short, not in short, but full proof I am giving. So let G be a group of order P square Q square, and NP is the number of Sylow subgroup of G. So NP divides Q square and NP is equal to 1 plus TP. So NP is equal to 1 Q or Q square. So if NP is equal to Q square, then 1 plus TP is equal to Q square, which implies P is divides Q square minus 1, which is not possible. And if NP is equal to Q, then 1 plus TP is equal to Q implies P divides Q minus 1 implies P divides Q square minus 1, which is also not possible. Therefore, NP is equal to 1, so there is only one Sylow subgroup in G. Let this subgroup be P. So then P is normal subgroup of G. Similarly, G has only one Sylow subgroup, say Q, and is normal in G. Since any group of order P square is abelian, P and Q are abelian. As before, order of PQ divides the GCD of P square Q square, which is equal to 1. Therefore, P intersection Q contains only one element. Therefore, P intersection Q is equal to identity. But the number of elements in PQ is same as order of P into order of Q by order of P intersection Q, which is same as P square Q square, and is same as order of G, which implies G is equal to PQ, because PQ is a subset of G and both of them having the same number of elements. So similarly as before, A is in P and B is in Q, then you can write it in two different ways, and using the normality of P and Q in G, we get AB A inverse is in AB A inverse B inverse belongs to P intersection Q, and P intersection Q contains only identity. Therefore, we get AB is equal to BA. That means if A is in P and B is in Q, then AB is equal to BA. And since G is equal to PQ, P and Q are abelian, and AB is equal to BA for all A in P and B in Q. Therefore, G is abelian. That is for the day. So in the next session, we discuss about the classification of group of order up to 15. Thank you.